Hey guys, what is going on? It is your good buddy Sam, and this is going to be, if you can believe it, the third Max video in 3 days. For me, it's a personal accomplishment, and I have to say too that I think it might be the most productive that any human being has ever been in human history. It doesn't seem like any person could be this productive, but somehow we've managed to do it. I don't know what to tell you. So what I'd like to talk about today, we've been on this thread talking about Gen and doing physical modeling, this kind of stuff. And what I want to talk about today is shaders. So specifically, I want to talk about, well, graphic shaders and just how to do even some simple stuff. The kind of things that you can do with shaders is absolutely unbelievable. In case it's not a familiar concept to you, a shader is just a program that you use to address, or that runs on your GPU rather. And the GPU is the part of your machine that can do an incredible number of parallel computations, and it's what makes modern graphics possible. As I said, you can do some unbelievable stuff with it. We're going to do some stuff today that's very, very believable, but maybe it's the first step towards something cooler. And what I'd like to do actually is build towards something that I know for a fact it's going to be pretty cool. So we'll take it in stages. And what I want to do today, very simple, just take an object and shade it in a way that, well, we find aesthetically pleasing, hopefully. So to get started, I'm just going to make a jit.world. And jit.world is, as we all know, it's the window combined with a renderer, combined with a few other things, but the window and renderer is the important bit. And then I'm going to do a jit.gl.gridshape, the shape that we're going to be applying a shader to, and then just jit.gl.camera so that we can change the position and move the camera a little bit further back from the object so we can see the whole thing. And believe it or not, already we're ready to save this, and that's because I want to have a Max Patcher and also a shader file side by side in the same folder. Side by side in the same folder so that Max can find the shader. So I'm going to make a new folder on the desktop called Shader Tutorial, and then save this patcher in there as Shader Tutorial. And then make an object called jit.gl.shader, and this is where the action is actually going to be happening. I'm going to give this a name too, @name stripes, and move it over here. And double click on it, and this opens up the actual shader text. So let's see, the patch actually doesn't do very much interesting, so I'm just going to move it over here, and I'll move the graphics context here and move the text over here. And in case you want to make this text bigger, by the way, I learned this just today. I've been using Max since what feels like the dawn of time, and I've only now learned that you can go to Object, Show Fonts, and then bump the size. And now we can actually see, or hopefully you can actually see this program a little bit better. Cool. So now, sorry, I just need to come to this grid shape and do @shader stripes. And because this shader has the name stripes, and because this grid shape is referencing @shader stripes, now our shader is what's determining the way that this sphere looks. And I just need to now save this. So this is the default shader that just colors it flat gray like this, that Max loads by default when you make a JitGL shader object. So I'm just going to save this and save it side by side. So we'll just call this stripes.jxs. .jxx is the extension for a jitter shader. And if I save this, now you'll see that the name stripes.jxs is up here. And if I close this and then double click on this, there's my stripes file over here. Cool. So now we're ready to actually do the interesting part. If you look at this and you've never seen a shader before, you might be saying to yourself, oh my holy geez, what is going on here? Don't worry, we're going to go through it. It's not that complicated, or it is a little bit complicated, but the important bits are actually here. This is called the vertex shader, and this is called the fragment shader. As you probably know, this sphere here isn't a true sphere. It's actually made up of a bunch of triangles, each of which has 3 corners or vertices. And what the vertex shader does is it walks through each vertex. Well, I say walks through, it makes it sound like it sounds as if there's iteration happening, but in fact, it all happens in parallel. It goes through all the vertices and computes two things. The one thing it has to compute is it has to compute this thing, GL position. And this F transform function, what that does is it converts from the vertex position, which is to say the position of a point on the edge of this sphere relative to the sphere, and converts it to a position in sort of the camera world. So, you know, a point on the sphere has some position relative to the sphere, but this GL position is where it appears relative to us looking at it. And it passes that onto the fragment shader, which then actually gives each, so the vertex shader iterates over vertices, the fragment shader iterates over pixels and gives each pixel a color. So, it's easy now if we want to change the so the fragment shader has to set this thing called GL frag color, and we can set it to something other than GL color. We could set it to, for example, vec4 1 0 0.0 0.0 1.0 to make I just saved here and it automatically recompiles and of course shades the sphere red, because every pixel is now being shaded red. And we actually don't need this GL front color thing anymore because we are making the frag color ourselves down here. So suppose, well, I already told you that what the vertex shader does is compute this GL position, but it is also allowed to compute anything it wants and then pass that data over to the vertex shader using what are called varying variables. So what I'm allowed to do is something like this. I can declare up here above the definition of the vertex shader, I can write varying float v, and then the same down here above the fragment shader, varying float v. And now if I set this v to something here in the vertex shader, it will be available down here in the fragment shader. So what I can do, for example, is I can do v equals GL underscore position dot y. And then one thing so now what I could do is I could take this v, and instead of 1.0 here for the red color, I could say v. And if I save this, what you'll see is that the top half of this sphere is now colored red, and the bottom half is colored black. And if I make a jit.gl.handle, jit.gl.handle, and attach this to the grid shape so I can move the shape around, if I move the shape up and down, you'll see that I can make the whole thing red or the whole thing black. There's kind of a line right at about between 0 and 1 where the shape becomes more and more red. And that's exactly what you'd expect. I've set this v equal to the y coordinate of a particular point on the edge of this sphere, and then pass that through to the fragment shader and use that as the red color for this sphere. And this is the basic idea behind what I want to do, which is give this sphere some stripes. So, how are we going to do that? Well, the first thing you need to know about stripes is that stripes are striped. And that sentence probably didn't give you a lot of information, but what I mean is that a stripe function looks kind of like this. And now we switch over to this other, have you guys heard of Illustrator? It's a pretty sweet program. So what a stripe, imagine you have an object, and the object has some stripes. I really wish I had a Wacom tablet or something. Anyway, imagine this object has some stripes, and then imagine you were looking at just a slice of the object, say up the vertical like this. What you might see if you drew the stripes as a function is you might see something like this. A 1 everywhere where there's a stripe, and a 0 everywhere where there's not. And it won't surprise you to learn that this, or what am I trying to say here? It'll be a familiar shape. It's just a square wave, right? We've seen square waves before. We've done things where we take an audio signal and change it from one shape to another. So all we want to do is take the position of the, say the y coordinate of this thing, which just looks like a rising ramp, and somehow make it look more like this. That's all we're going to do. So the first thing that we're going to do is come down here in the fragment shader and take this v and compute the fractional component of it. So we'll do float sawtooth equals fract v. And if I take this sawtooth now and use that in place of v, save this, What you see immediately is you see that this shape already has something kind of like stripes. What this fract function does is it gives me just the fractional component of v. So if v is 12.2, it gives me 0.2. If v is 0.7, it gives me 0.7. If v is 1012.9, it gives me 0.9. And what that ends up doing is taking a long rising ramp like this and turning it into something more like this, a sawtooth wave. So now we're going, of course, between 1 and 0. So now what we want to do is convert this sawtooth wave into something that looks a bit more like stripes. One way that we can do that is we can take our sawtooth wave. Somehow I can't draw triangles. Take our sawtooth wave and convert it into something that looks more like a square wave. So what I'm going to do first is take this whole thing, multiply it by 2, and subtract 1. So that instead of going between 0 and 1, it's going to go between -1 and 1. So that'll look like this. And apparently if I stay completely silent while I draw, then I'm able to draw something that a third grader could draw successfully. So I'm going to convert it to look more like this. And then lastly, I'm going to take the absolute value. And what that will do is take all these parts that are negative and basically just flip them up so they're above the horizontal. And what that's going to look like is something more like this. Takes every ounce of concentration to draw this. But something more like this is the goal, where this is 1 and this is 0. So the steps are take the ramp, which we already have, multiply by 2 and subtract 1, and then take the absolute value, and that will give us a triangle. So I come back to max. Where are you, max? I come back to max, and then I do float triangle equals sawtooth times 2 minus 1, and then take the absolute value of that whole thing. And then if I color this using the triangle instead of the sawtooth, like this, now you see we've got these things that almost look a bit more like stripes. So we're getting there. What I could do though is I could give these stripes a little bit more sharpness, and we can do that using an object called, or a function rather, called smooth step. So we've already got this triangle thing here. And what I'd like to do basically is say, okay, everything in this range from, say, 0.5 and greater, let's just call that 1. And everything that's less than 0.5, let's just call that 0, right? That seems a pretty decent way to get a stripe. But there's also this function called smooth step that's basically going to let me apply a little bit of feathering sort of in between. But I'll show you kind of what that looks like. If we come down here and just do float stripe equals smooth step 0.5, 0.5 triangle, and then save, and then use this stripe value here instead of triangle in our vec4, save. Now we get these really, really harsh, well-defined stripes, right? That's because the smooth step function it describes a sort of threshold, and anything below this value is going to be 0, and everything above this value is going to be 1. But then it lets you say, if these values are the same, then it's just a harsh transition, right? It immediately goes from 0, values that are less than 0.5, to 1, values that are greater than 0.5. But if these values are not the same, then you can basically get a little bit of feathering. So if I do something like float bleed equals 0.1, and then change this to 0.5 minus bleed and 0.5 plus bleed, now you can see there's a little bit of blurriness on the edge of these stripes. And if I make the bleed 0.5, now there's a lot of blurriness. If I make it 0, now there's the same harsh edge from before. I'll just do 0.1 for now and leave it like that. So there we go. We've got our stripes. If we wanted these stripes to be a little bit more numerous, we could take this V here and just multiply it by 10, say. And I don't know what I typed, but that's better. Yeah, multiply it by 10 or maybe like 4, get a few more stripes. I'll leave it multiply it by 1 for now. So what I want to do, we've already got our stripes, and it's pretty sweet, but I want to play around a little bit with this, how we calculate the position up here. So what you'll notice if I start to move this object around now, is that as I drag it up and down, the stripes stay in place, right? So we're using the GL position, but the GL position is the position of the vertex in the eye of the camera. So it's where the, you can imagine that this GL position is like a huge grid, a fixed grid with the camera's world, and we've sort of colored different slices of that world. And as I drag the sphere through that plane, or you know, around in the camera's world, we're just revealing different slices of a sort of world that we've colored in the camera matrix. And that's why it's kind of, these stripes are almost look like they're not really part of the sphere, right? What if instead of using the GL position here, I use something called GL_vertex, and then save this. Now we're using the position of points on the sphere rather than the position of coordinates in the world to color the sphere. And if I move the sphere around, you'll see that the stripes stay fixed in place. And that's because in the coordinate system of the sphere, none of the vertices are actually moving, and hence this coordinate, or this parameter v, isn't changing as I drag this sphere around, which I think is pretty neat. So one thing that you can do that's kind of cute, already I'll just say, okay, what if I make this into GL_position again, and then you can do something like say, so what I'm trying to say here is that we're kind of done already, like you got some stripes, but if you want to do something cool, you can always, a cool way to kind of make weirdness happen with shaders is always to take anything that's based on the position and then mess with the position, and then you can make some interesting stuff happen. So say for example, instead of taking the position.y, I take the sine of the position.y and use that as my v. Not so interesting, but maybe if I take this and multiply it by 5, now already we've got something kind of interesting going on. And as I rotate this shape, there's definitely some weird stuff happening here. So what you can do, though, is take this thing, which is already kind of cute, and then if to this you actually add the GL_vertex.y, for example. So we're combining the vertex and the position. Remember that one of these, the position, this moves as the sphere moves. This, the vertex, doesn't move as the sphere moves. And so if you take the sphere and you move it or rotate it, then these two things, these two kind of systems, the position and the vertex, are kind of sliding against each other, and you can get some interesting sort of patterns going on here in your shape. So I'm just going to take this grid shape and do something like jit.anim.drive, just to do an automatic rotation, and do something like turn 0.1, 0.13, 0.1, I don't know, 43, and start turning this thing. And you just get these kind of like cute wavy sort of patterns as the shape rotates against itself. You could always come in here and make there be maybe more stripes by multiplying this by a larger number. That's kind of cute. You can try turning this into something bigger. You can multiply this by something as well. It's maybe too much. That's not cool anymore. Yeah, you can definitely make some wacky and kind of interesting stuff happen here. If you wanted to get really fancy, maybe like we compute a v, and we also compute a, what letter comes after v? W. And we say w is equal to, or v is equal to this, and w is equal to, I don't know, this times 2.7, but we'll use the x and not the y, and then we'll use the position.z, and we'll multiply by 37, just to make something different. And then take this varying float w up here and copy it down here so the fragment shader can use it. Doing all this just so we can take all this nonsense and then compute, this got, can I do this as easily as I wanted to do it? What if I just do like this plus w? Is that cool? No, that kind of sucks. What I want to do is, can I do this in a way that doesn't make this totally crazy in the time that we have left in this video? I think so. So what I'm going to do is take all this and abstract it out. So I'll make a new function up here. I didn't expect to do this. You can be done if you want, but if you want to stick around and see what happens, we can stick around. I'm just going to do float make stripe, and then pass into this function a float f, and then take everything that's between that's used to calculate the stripe, all this stuff, cut that out, and then paste it up here. And instead of using v in this fract calculation, I'm going to use f. Why do that? So now in this main, I can do something like float stripe red equals make stripe of v. And I can do float stripe green equals make stripe of w. And then change this to stripe red and change this to stripe green. And it didn't work, which is exactly what I wanted. I wanted it not to work. Why didn't it work? Missing return. Yeah, you big doof. You have to return stripe. There you go. And see, that's kind of not as cool as I thought it would be. But, well, we'll get there. We'll get there. It's the first video. We've got a lot to learn about shaders. I don't think that this has to be the coolest thing that ever got made. But in any case, thanks for watching. Excited to talk more about shaders and physical modeling and lots of other cool stuff in the days to come. So thanks for watching, and I'll see you guys in the next one.